All right, good morning, everyone. My name is Zolltan Arato. I'm a product manager of Google Cloud IoT. Let me also introduce my co-presenters for today, Kerry Maletsky and Lucio Diasio, both from Microchip. All right, IoT security is solving the primary hurdle to IoT deployments. In this breakout session, we are going to show you evidence why connected product companies and IoT fleet operators find security a top hurdle, a top challenge. We will also talk about how and why these challenges ultimately come down to a question of cost and complexity. And most importantly, we will show you a toolset or give you a toolset, an end-to-end toolset that can help you solving these challenges. So let's take a look at our agenda. First, very quickly, we will touch upon the why the need is undeniable, why it's a top concern. Then we are going to talk about the theory, like the principles of solving IoT security. And probably the longest part of the presentation is about the solution proposed by Google and Microchip. So let's start by this number. This is an actual Gartner number, so this is not an estimation, and this is from last year, number of connected devices. So it's probably more now. I guess all of you remember those estimations from a few years back, predicting super high numbers of connected devices. Now this is real. This is happening. Our device is generating more data than ever, and that also means that the attack surface is growing rapidly. And important to highlight that these devices are most of the time resource constrained, and security measurements are close to non-existent many times. And there is evidence to that. So we see a clear acceleration of attacks. Probably the most well-known is Mirai. I'm sure many of you have heard about Mirai. It was a botnet attack 2 years ago. It hit low secured cameras, CCTV cameras, and performed a DDoS attack against DIN, one of the biggest domain name services in the US, and brought the internet down, or most of the internet down, for multiple hours. Just another example which happened this year. A hacker got into a casino using a thermostat of a fish tank. So not only DDoS attacks are a threat in relation to IoT deployments, but also these devices are connected to your network, so they can access their network. So if a hacker can go to get to your device, they can go into your network. What this really means to us is that IoT security is complex, it's challenging, it takes time to secure an IoT deployment, and it's not something you can do once your fleet is deployed. It cannot be an afterthought. You really need to take care of security before you deploy devices. So let's take a look at the challenges of IoT security. This is just a summary. We are going more into the details very soon. So strong device identity and authentication, how you identify your devices, how you authenticate them, how you use asymmetric keys for these, securing the manufacturing line, how you transfer keys. It's a complex process. How you protect your keys and how you make sure that the software ran by your device is what it is supposed to run. And key rotation, how to treat keys as ephemeral and how to update keys as needed. And of course, application layer security. It's very important, but we are not going to talk about application layer security. We are going to focus on the IoT related parts. It's not that it's not easy, or it's not that it's easy, but it's much more well described or discussed So we are not going to talk about that here. Even though most of these principles can be implemented using software only, a much higher level of security can be achieved if we involved specialized hardware. So that's why hardware plays a key role in secure IoT deployments. And that's also why we partnered with Microchip, because their offering plays a key part in what we offer as a secure solution for end-to-end deployments. So I would like to invite Kerry on stage, who will talk more about Microchip.
I don't know how many of you are familiar with Microchip. We've been around for 30 years, and we ship over 2 billion 8-bit MCUs every year, so maybe many of you out there have designed some kind of system, whether a PIC or an AVR microcontroller, and you're familiar with Microchip. You may or may not be familiar with the broader range of products that Microchip has. Among them, things like wireless and wired connectivity solutions, and analog devices, interface chips, and security devices. So all in all, that kind of gives us this idea of having devices that are smart, like an MCU, connected, wireless, which is really what IoT is all about, and secure, which we're going to make the case here is a key part of how you build an IoT endpoint, thinking about security at a hardware level. And obviously, Microchip has a good solution across that board. So let me just start and kind of reiterate some of the points that Zolltan made. It's hard to overestimate the importance of a device identity, right? When you get past all the 3- and 4-letter acronyms, you get all the words, everybody's all happy about what they got in security, you have an identity at an endpoint. It's a number. It's really all it is, right? There's a number. It's a digital world. If that number gets compromised, then you don't have a secure endpoint. Doesn't matter what protocol you use, doesn't matter what algorithm you use. If I can copy your number, your device ID, your key, whatever you want to call it, then I am you. All right? So everything we're going to think about is going to be, how do we take that ultimate root of trust, that a device key, and protect that in a way that then we can build upon that to build a secure system. And so to do that, you need a couple things. You need to be able to verify that identity, and obviously if I just send you my identity and send over the network, I'm Kerry, well, everybody knows that, right? You can look that up. So that's not really a very good identity. It needs to be something that can be verified without being disclosed. Trustable, unique. Obviously, it's no good if there's a lot of Kerrys out there. There probably are. So there must be something different about me than the others. We'll talk about that. This isn't to talk about cryptography, but let's just say that asymmetric cryptography is a good solution for this approach. Maybe we'll store a private key as an identity. We'll use the public key as a way to validate that. I won't talk too much about how the mechanics of it work, but you'll see how that plays out as we go forward here. So okay, we got this, this number, this digital ID, this private key, whatever you want to call it. I said that's what everything is about. That's what's important. Well, how do you get it in your gadget, right? How do you put that private key into your device in such a way that, well, ideally not too many devices have copies of the same private key when you mess up? You know, you've got a diverse manufacturing environment. Maybe you've got subcontractors on 3 continents. Maybe one guy builds one part of the system, other guy builds another part of the system. Maybe next year you have a different subcon than you got this year. How do you manage that environment in such a way that the way these identities go in your device can really be trusted? They're all unique. So this is a pretty complicated problem, and let me propose a solution that says, I don't care where you manufacture. Let's move that identity process, that identity assignment process, out of the manufacturing subcons into the supplier of the semiconductor. So you take a secure element, secure chip, same thing, and the manufacturer of the secure chip, in this case Microchip, we program that identity in it. So when it shows up at the manufacturing sites, at your subcontractors, it's already got that identity. And let's go one step further than that. Let's build not only the identity, but the relationship between that identity and something else. That relationship might be manifested in a certificate. That's a traditional PKI scheme. It might be manifested in some kind of a registration scheme. That's what we'll talk about a little bit later in the presentation. But So an identity and a relationship pre-built into that chip, so no matter where you build it in the world, you get that same trust of it's unique, nobody was watching when you put it in the device. Okay, so we got an identity, we got a way to get it in your gadget. But wait a minute. Then the gadget's going to go out in the field. There's going to be jillions of these things, right? You guys are all big, successful companies. You're going to sell millions and millions and billions of devices, and everywhere around the world is going to be your device. And because you're so successful, a lot of people are going to want to try to copy your device. And if they want to copy your device, they need to get that digital ID out of one of them, and then they make 50 copies of that one, or maybe get out of 100. So you really don't want them taking the digital ID out of your device, and you've got to protect against that. One way you do that, or maybe the only way to do that, is to provide some kind of secure storage for that private key, that secret. And let's just say that you really don't want anybody to mess with it. They can't copy it, they can't change it, they can't delete it. Any of those things are really bad. Once that happens, then the device really doesn't have a connection anymore to the network, right? So that's good, but it's not enough. You got to protect what your device does. I got the temperature sensor, I've identified that it's in room 12, but if I can change the software, well, yeah, I'm talking to the thing in room 12, but no, it's not really giving me the temperature. It's giving me a bogus number, right? So you got to protect the firmware. There's lots of ways to do that. Let's just say one fairly traditional way is to verify a signature over that code every time the thing boots, right? So it's hard to change the software. You know, hard to like replace the chip without getting the thing to reboot. So let's verify a code signature at boot. A lot of people call that secure boot. That seems like a good answer. We'll connect that a little bit later to hardware security. Now, Zolltan made a mention about key rotation. And you might say to me, whoa, you just said you're going to store this thing really super secure, nobody's going to be able to touch it. Why do I need to rotate it? Hey, nobody can mess with it. Well, there could be sort of rules, regulations, policies that demand it. That's okay, right? We all got rules we got to follow. Sometimes they don't make any sense. That's just life. So there could be policies, there could be limits. Every algorithm has a limit on the number of times it can be used before the key is no longer considered to be valid. So that's okay, I don't mind that. But so you want to be able to do this rotation, but at the same time, you can't think that rotation is a substitute for security, right? If I say, well, I don't need to secure the key storedly because next week I'm going to have a new key, so who cares? It's only 1 week. That isn't going to work, right? Because the bad guys are going to find it not next week, not next day. They're going to find it 3 seconds after you rotate that key. And if you don't have a way to protect that key for that week, that year, that month, that 10 million transactions, then you still don't have security. So key rotation is important, got to do it, but it's no substitute for sort of an environment in which you didn't have to do it. So think about that. There's lots of ways to do that. I'm not going to talk about it too much. PKI or asymmetric cryptography gives you a couple of ways. You can either generate new keys and sign them with a trusted key. You can use a derivation mechanism. There are lots out there that are good. You could store multiple keys in your device. You could ship it with 10 keys, and we could say, I'm going to use the keys at random, or it's got a 10-year life cycle. I'm going to use the first key for the first year and the second key for the second year. However you want to do it, that's fine. It's all good. And the cloud is going to manage those policies, right? So the cloud understands the trust relationship. The cloud understands the architecture of the device, and the cloud can say, okay, hey, I don't like that key anymore. Let's go on to the next key, right? So that's a good thing about having the cloud relationship. No longer does the device have to be able to say, hey, I don't like this key anymore. Now the cloud can manage that. So, Zolltan touched on this. You build your system, you got all kinds of software, you love all your software solutions, you got this stack, you got that stack, maybe you download some software. But at the end of the day, there's that thing that I started with, that digital ID, right? It's got to be used. You got to put it as input to some complicated algorithm. And that means the software's got to touch that. So there's a piece of software that has access to that digital ID, that private key. Well, so if one piece of software can touch it, how are you going to prevent other pieces of software from touching it? Oh, you got an OS, you got kernel code. Yeah, sure. We all know all kinds of exploits, which allow things that you wish wouldn't touch stuff to actually touch them. So, especially in the IoT world where, you've got these complicated things, you got all these stacks doing all these different things, but you're a temperature sensor, right? You just know what's the temperature in room 12, but it's really complicated to do that, right? So what we're going to propose here is I'm going to isolate those private keys from all of the software. I'm going to say no software can touch the private keys. I don't care what software you have. Good, bad, big, small, purple, green, doesn't touch the private key. And by doing that, it leaves a lot of questions, a lot of problems you have to validate, takes those away, right? And by the way, it's not that we don't like users, it's not that we don't trust them, it's that they make poor choices, right? Okay, how many of us have ever logged on and created a password that may not have been an optimal password, right? Once or twice, it happens, right? So you can't really trust users. It doesn't mean they're bad people, it doesn't mean they're untrustworthy. It just means that they make choices that may not be consistent with security. So, not going to let users see it, not going to let software see it. And, you know, when we talk about hardware, you might think, oh, I got a microprocessor. That's a piece of hardware, right? Nah, not really. Microprocessors are typically not designed to protect keys in a way that an aggressive attack might get them. And I'll show you in a minute what an aggressive attack means. And if you think about it, if you connect all these dots, now, that means that it's also protected in the manufacturing phase, right? Because even the manufacturer doesn't have a way to attack it, right? So you've got some subcon soldering chips on the board. Doesn't matter. He could be just as untrusted as some guy out in the field who hacked the sensor off the wall of room 12, right? So totally protected during the manufacturing phase. So, okay, that's nice. These are all nice concepts. Now, how do we build that into something that's useful that we can ship to customers, that connect to the cloud and do a useful thing? It's got to have value, right? So first thing, use a secure chip. So I'm going to talk a little bit here about the ATECC 608A. So I won't say that too much, you know. Think of it as a secure element, okay? It's a secure chip. Think of it as an electronic safe. What's it going to do? It's going to do, of course, it's going to store that digital ID, right? It's got some secure double E problem. It's going to put the key in there. It's just a key, right? It's just a number. It's going to store that there. And it's going to include enough crypto engines on it so we can act on that key without having to divulge the key. It wouldn't be very interesting if I had to send the key out, right? The key never, ever leaves the chip. You want to do an authorization, you want to do some kind of validation, you say, okay, hey, prove that you have that secret without divulging the secret. And so all of that's done inside this boundary. So there's a hardware boundary. You try and get through the boundary as an attacker, and you can't. Right? So it's all encapsulated. There's no software inside. It's not something where you write the code, and maybe there's some bugs in the code, right? It's all a turnkey solution. And I'll just point out the red box over there. I like to point this out because everybody thinks, well, random numbers, you know, I don't know, just get some keystrokes. Doesn't matter, right? Well, I mean, actually every single cryptographic protocol out there, one way or the other, requires random numbers. And random numbers are really hard to generate. So my favorite definition of a random number, one that's never been generated before and will never be generated again. Right? That's a random number. It's maybe not a technical description, but it's not a bad functional description, and it's really hard to do that in a way that you can trust, right? Everybody's got their multi-gigahertz, multi-core processor. Think how many times you can try different numbers. So if you want a number that's different this time than last time, it had better be really good. And it's really hard to do that. So I'm going to put all those things inside this box. And I'm just going to have a simple interface to it, right? I2C, one wire. So easy to talk to, but hard to get inside. So that's the kind of basic concept of a secure element. Okay, I got this. What good is it? Because it's all by itself, right? That's not the temperature sensor in room 12. That's just a little box with a device ID in it. How are you going to use it? Well, you're going to connect it to whatever you've got on your system. So you've got some kind of processing element. Maybe it's the Edge TPU that just got announced. Maybe it's an MCU, an MPU. And that guy is going to talk to it. Now, the slide here, you know, shows something like where the MCU passes a challenge to the chip. The chip responds with a response, and the MCU has some way of verifying that. That's a fine answer. What we're actually going to show later in the presentation in the demo is the cloud sending a challenge down through the microprocessor to the chip. The chip responds, sends that response back through the microprocessor up to the cloud, and then the cloud decides whether it's going to accept this transaction, this relationship or not, right? So I said at the beginning that asymmetric cryptography and private keys make a nice way to think about a device ID. I stand by that. It's beautiful. But there are downsides to PKI, and some people like symmetric or shared identification as well. I'm totally cool with that. That's a good idea. There's a time and a place for that. So that challenge and response, it could be a challenge in a signature if it's asymmetric. It could be a challenge in a MAC if it's symmetric. Those are perfectly valid things, and I would never say that one is more secure than the other. One may be more appropriate than the other, but they're both secure ways to accomplish this problem of verifiable identification, right? And then let me just make a small point for those of you out there who have designed PC boards and the like. This is a tiny little thing, right? It's not your video processor with 300 IOs. It's a tiny little box with a couple of wires for IO. And when Lucio does his demonstration, you'll see it's probably the smallest chip on the board, even though it has the most security of all those chips on the board. So, okay, we're going to think about this secure element now. It fits whatever your endpoint looks like. I don't care whether it's got a 32-bit, 64-bit, 8-core processor, or it's an 8-bit single-threaded machine with K bytes of memory. Doesn't matter, and everything in between, you can put this on that board, and now you've got a root of trust that you can trust separate from all your software, from all the other pieces of your system. So, key protection, you know, great. I'm up here, I'm selling this thing, I say, hey, it's really strong, the keys, trust me, right? Well, I mean, maybe you don't. So how is it that people get these keys out, right? I mean, lots of software attacks. Zoltan's slide showed a bunch of different software attacks. But you know, if you're making 1 billion gadgets, you got a lot, somebody else would like to steal your market, right? 10% or 1% of your billion gadget market is a big number. I'd really like to have that as a bad guy. And so I'm not going to stop at some published attack, right? I'm going to do all sorts of crazy things. Like this particular crazy thing I got up there is a microprober. You know, you could scrape the top off the chip. You could put some needles down on the chip. And trust me, this is not a complicated thing. You can buy microprobers on eBay. You can use them in your kitchen. It doesn't really require anything too complicated. It's really, you just kind of probe down. You know that JTAG lock that you got on your processor? You hit that bit and no more JTAG, right? Unless I put a microprobe down on that JTAG wire and I pull it high and say, oh, now I do have JTAG, and I reuse JTAG to read the key out, right? So if you get a secure element, there's a picture of it, sort of a piece and a blow-up of a piece of that. You know, secure elements typically will have a shield, so that serpentine thing on the side covers the entire chip. There's nothing to look at. And the signals that are going through that have nothing to do with cryptographic or identity. They're just random signals that we check, and if you short them out or cut them, then the chip stops working and it's dead. But, look, I'm only showing this particular attack because it really looks good on a slide. Right, there's pictures, shields, stuff like that. There are way better attacks than this one. This one's complicated. You know, probably people are going to notice if you kind of take your thing apart and strip the silicon off. You know, my favorite sort of non-visible attack is some kind of a side channel attack. You put a resistor in series with the battery. You do a single trace, or maybe multiple traces, of the power signature during a cryptographic operation. You take that trace away, you put the battery cover back on, hang the thing back on the wall, and now at your leisure, you analyze that trace. And using that analysis, you can find the key. And so if you think that anybody's microprocessor won't leak data when it's executing code, this isn't the right slide presentation, but I got some really good ones to show you how it's done. It's actually not that hard. So there are hundreds of different attacks, and you have to defend against every one, right? Because, of course, the attacker is only going to do the weakest link. Whatever one thing you didn't defend against, that's what the attacker is going to do, and it won't matter that you defended against the other 99. So you need to have a way to protect these secrets that defends against everything, right? Attacks you've never heard of. And so that's probably not going to happen by default. It's going to happen because somebody has spent, you know, careers and teams working on just that problem. And so that's what a secure element does, right? The whole point of using a secure element like this is that that's all we do every day, is think about how the bad guys are going to try and get the secrets out. We don't know anything about temperature sensors, really. All we know about is that bad guys are going to try and get the secret out of our chip. We don't want to let that happen. Okay, so let's kind of build that up now into an IoT thing. Yeah, so this is sort of how IoT devices look, right? Right, you got some application, your IP, the thing that makes your device special. You got some sort of cloud connectivity stack, ideally connectivity to Google Cloud, right? Because everybody wants the cloud. I mean, without the cloud, how are you going to get to your device? What good is it? You've got some sort of operating system. Maybe it's a real-time operating system, maybe not. You got some big processing element that's running your communication stack and your security stack. In this case, I'm looking at something like TCP/IP and TLS. They're common things. There are other ways to do it. And then you got some radio, some wireless hardware, and some sensors to do your thing. It's kind of how that's how an IoT device looks, right? That's how it's done. But, let's think about it for a minute. In the world, there's a big variety of architectures and cost points and power points for embedded systems. You got, everybody's holding up the red one in the top, right? You got some big multi-core processor with gigabytes and fancy OSs, and that's great. There's a place and a time for that. I wouldn't want anything less in my pocket. But that might not be the right answer for the temperature sensor in room 23. Maybe you want something that's a little bit lower cost. So you could think about something in the middle, some kind of RTOS sort of thing, maybe a little bit more restricted operating system, maybe a real-time operating system. It's a good thing. Millions of those units are sold a year, but you really like Zoltan's slide about that 8.4 billion and that curve. How you want to be on the billions of sides, right? You want to sell billions of devices. If you're going to do that, and if you're going to consume that data, right? If you're going to think about how do I manage the heating and cooling in a building with 1,000 rooms, I need 1,000 temperature sensors, right? If I want to manage some kind of a factory with 1,000 valves, I need to know each one of those valves. I need to control them, right? So now we want to think about these billions of units where you want to power them with 8-bit processors. And so AVR and PIC microprocessors are probably the kind of processors you're going to use. They're the number 1 and number 2 processors in the market. But these are very resource-constrained things. Don't think gigabytes of memory. Think kbytes of memory. And don't think, how big is the power supply going to be? Think, can I make that battery last for 5 years without replacing it, right? So we're talking about a totally different environment here, and this is the thing that drives that 8.4 billion number, right? It's this constrained environment. So how do I simplify the development of an IoT device so that I can build those small devices and I can get them to market in a timely manner? Because the other guy's trying to build the same thing, right? If I don't get there sooner, he's going to take my market. So let's redraw that picture a little bit differently. You still got your application software, whatever makes you special, you still got to do that. You got some kind of cloud connectivity stacks, but now let's reduce that to the component pieces necessary to talk to a stack. Here's the component pieces for Google Cloud. And beyond that, now we're going to really start to change things. We're going to say, okay, I want a development environment where I can automatically generate the drivers I need, right? Because really, I only care about the stuff in yellow or orange or whatever that color is up there. I only care about what's my IP. I want to push the button, one click, and get all the other stuff done. And at the lowest level, I want to split the security and communication stacks away from my processor. I want to focus on writing the software in my processor, my MCU, that does what's important to me, processes that temperature, right, with a number. It's not that complicated in a sense. And I'm going to leave the security stack. I'm going to put it in a secure element. I'm going to take the connectivity stack. I'm going to put it in a wireless element. And now I'm going to build a much simpler and more secure IoT element. And I'm going to get to market faster because I'm going to do it with much less software and in a development environment where I can push a button and get it done, right? And that's what we're all about. So, just so you don't think this is vaporware, I mean, it's a good concept, but if we can't reduce it to practice, then that's not so interesting. So Lucio's going to show a demonstration later where we connect these 4 things. The demonstration happens to use this particular AVR microcontroller, but this concept, this architecture, this software works with any one of the thousands of microcontrollers that we and other people sell. What we offer is a one-click software development approach. So it doesn't matter which of the processors you use, you push that button, you get the software stack necessary to do it. The secure element that we've been talking about here implements all the algorithms, whether it's symmetric, whether it's asymmetric, to do that cryptography, secure that key, and to isolate your software stack from all the cryptography. So, for instance, I talked about secure boot, validating your code image. Well, that secure element can validate the signature. So instead of you having thousands of bytes and maybe minutes of code execution time, you push that hard stuff off to the crypto processor. It does that software stack. Same for Wi-Fi. This particular picture shows a Wi-Fi chip. We got solutions with other networks as well. The one we're showing here, despite the congested Wi-Fi environment, is the Wink 1510. It's got the TLS and TCP/IP stacks built in. So you don't have to think about that in your application, right? Think about it as a UART. Send some bytes, get some bytes. And it all would be useless if there was nobody to talk to. So it's all set up in the same way to talk to Google IoT Cloud. And so now you've got this easy-to-design solution with an easy-to-use cloud environment, and that's exactly what your customers are looking for. And it's highly secure. So when you go down and attack it, you're not going to get that private key. So let me pass off to Zolltan.
Thanks, Gary. So just to reiterate, there are two sides of providing a highly secure end-to-end deployment, a secure chip, and the cloud. So let's talk a little bit about the cloud side of things. So 3 key challenges we kept in mind while building an IoT solution and while developing cloud IoT. Secure device connection, probably needless to talk more about this, that's the topic of the presentation. Scaling on demand, meaning you start with a prototype, you deploy 10, 20, 100 devices, and when you feel like it's time, you can easily go to 1 million. And actionable insights, so these devices generate lots of data, and you have to look behind that data. What kind of analytics you can get out of that data, what you read out of that data. And so these are the principles we kept in mind while designing Google Cloud IoT. So this is just an overview of Cloud IoT Core and the whole ecosystem around it. Cloud IoT Core is our solution for connecting devices, managing them, ingesting device data, and sending configuration and device updates to them. So you can see our edge solution here. We just announced it. I'm not going to talk about it. We don't have time for that, but please check it out online. It's really cool. So what you can see here is we have these edge device, we have these end devices, and then our edge solution, and then the cloud side of things, Cloud IoT Core. It's directly integrated with PubSub, our solution to channel messages into our cloud service, other cloud services, so like Cloud Functions or data flow, and then to store them in one of our storage solutions or visualize them using Data Lab or Data Studio. The network, very important to talk about. One of our strengths is our network. When it comes to an IoT deployment, latency is crucial. So Google is actually the only non-ISP company owning submarine fiber. And this network that we own enables us to provide super low latencies. And you get this out of the box if you start using Cloud IoT Core. Just a little bit more details about Cloud IoT Core. There are 2 main components: protocol bridge, MQTT and the HTTP bridges. That's where devices connect. That's where they can send data and receive configurations or commands. It's super scalable, and it's directly connected to PubSub. And of course, the scaling is automatic. The device manager is for managing the devices, managing configurations, access control, and there is a nice UI as well for managing your devices, but also API support is available. So security, let's talk about the authentication, because this is really unique in our solution. So we are using a JOT-based authentication. The device has the private key. It signs a JOT token using its private key and overloads the password field of the MQTT Connect message with this JOT token. So essentially what happens is that we are providing a mutual authentication without the well-known TLS mutual authentication protocol. Now, of course, this requires the public key, the corresponding public key, to be registered in the cloud. So that has to happen before the device can authenticate itself with the cloud. And so once again, this is unique because you essentially get TLS mutual authentication functionality without having to have the full TLS stack on your device. So that can save resources on your devices, which is a usual problem in case of resource-constrained devices. All right, so let's take a look at the, the basic provisioning flow, how you register devices. So the provisioner, whoever the provisioner is, creates a key pair, stores the private key in a device, and then registers the public key together with the device ID in the cloud. And then the device can connect by signing a JOT using its private key to the cloud. Now this looks simple and good, but this is not the most secure solution, and that's because the key pairs are generated using software, and we just discussed that using a secure chip is a more like a highly secure solution, a more secure solution. So this is how the flow looks like using the secure chip. So the difference is really that the secure chip is added to your device. It already contains the public keys, and whoever is the OEM is, whoever manufactures the devices, receives the public keys as a file and can run a script to register these devices. And then it's the same process when it comes to the connection of devices. Now this is highly secure. It's simple. It all looks good. But is this enough? No. So there are still challenges here. So there are two main areas of challenges. One is key management. How do you secure the private keys in case you do not use a secure chip? Because not everyone is using a secure chip. But even if you use a secure chip, how do you transfer the public keys from the secure element provider, like Microchip, to the OEM, to the device manufacturer? The other big area of challenges is device management. How do you map the public keys to projects or registries? So how do you define the location of your device in your cloud project? And these decisions have to be made at the time of manufacturing. So overall, it's a complex project. And to tackle these two problem spaces, we are happy to introduce Cloud IoT Provisioning, a new service available as part of an early access program, so you can apply for it. And it's essentially an interface connecting secure element providers and device manufacturers, OEMs. So secure element providers can upload public key data into the cloud directly. And these public key data, together with the corresponding secure element ID, is available for the device manufacturers. So device manufacturers can create and assign targets for these secure elements. And probably most importantly, it provides a way to create generic devices which for which you don't need to set the target information, the project, the registry information at the time of manufacturing. They can download this configuration as part of the first boot. So let's see a demonstration of this. All right. This is the Cloud IoT Provisioning early version interface. As I mentioned, there are two personas here, the SE manufacturer, so secure element provider, and the OEM. And in this case, the secure element data is already uploaded. So I'm going to use this as an OEM, as a device manufacturer. I'm going to claim elements based on real ID. So real is a set of these secure chips. And I already have an ID prepared here. So I have claimed these elements. So you can see that these secure chips are now listed, and I can assign them to a target. But before I do that, let me open the console here. So this is a Cloud IoT core. I have, if all goes well, I have a registry prepared here. And you can see that there is only one device in it. Okay, this one. Now I go back to the provisioning service, and I'm going to assign these devices, these secure elements, to a target. What is a target? A target is essentially a project ID, a region, and the registry ID. I have one prepared here. So let's do it. All right. So now what happened is that I have added these devices to the project. And we can see the devices are here. So one part that I didn't demonstrate is that, as I mentioned, these devices can download their configuration as part of the first boot. I cannot demonstrate that right now, but that's also part of the solution. Cool. So with that, I would like to invite Lucio to the stage, who is going to show us another demo.
All right. Thank you, Zoli. So I hope you can hear me. I'm Lucio Di Iasio. I work for Microchip Technology, and I have to say I love software, don't get me wrong, but I like when software really starts touching hardware. Then the fun begins for me. So I'm here, and since we are at Google Next, I do the Google thing, which is I'm going to show you something new. It's going to be a sneak peek into a product that Microchip is preparing for this fall. And you get the privilege actually to see it in action. So it's going to be a live demo in front of you. So this is a concept that we've been working on to demonstrate practically the things that Zoli and Kerry have been describing in the presentation before. And so I'm going to literally actually show you a little board that is, here is the thing. It's 1 inch by 2.5 or so. And this is a concept that we came up with to try and demonstrate practically the effectiveness of a secure element and how actually ideal the Google Cloud solution, the use of the JOT, is for bringing cloud solutions, secure cloud solutions, even to the smallest devices in the pyramid of the embedded control world, right? So we want to take a secure solution to the cloud down to an 8-bit device. So I'll show you, maybe you can actually see it on the screen better. It's quite small, so I hope you can figure it out. I'll use a pointer here. And you'll see there's a debugger area. This is a full development system, if you want, inside an engagement board. And this is a complete system. Here you have the smart of the solution. This is a small microcontroller, just an 8-bit. You know, as Kerry said, Microchip ships 2 billion units of these chips every year. This is not a cumulative number. Every year we ship 2 billion of them. And this is what, you know, most bare metal embedded control solutions are made of out there in the industrial, in automotive, in all the fields. So this small 8-bit micro now is connected to the secure element. And I'm sorry, Kerry, your slide had the secure element as big as my chip, but it is the smallest thing on this board. The secure element is smaller than a temperature sensor, actually. Speaking of room 12, was it 12? So 23. So this is a temperature sensor. This is a secure element with all the crypto, elliptic curve, secure key management, and all the features built in there. And this is a light sensor, for example, that we added here. And also here you see a typical radio module. This is the Wink 1510. It's one of Microchip many wireless solutions. So all this connected on this board, and I want you to notice also this connector here, this pins here. And this is where you can actually plug in. This is a micro bus. So you can pick and choose between 450 additional sensors readily, off the menu, literally, and pick and choose and try to quickly prototype whatever your solution is. So maybe it's not just a temperature sensor in room 12. Maybe there's also a humidity sensor and a pressure sensor and a altimeter and whatever you want. So I will actually demonstrate how this board works, making it connect quickly to the Google Cloud. And so we designed not only just a board, that's easy, that comes fast. We designed a complete experience around this on how we can get a user quickly engaged with the Google Cloud. And so what I will do now is I will actually power up this board, and that should blink some LEDs. That's what you expect, huh? Is that pretty? I blink these 4 LEDs. Yeah, that's what we do in embedded control. We blink a lot of LEDs. And so one thing you might want to know is that, sorry. And this is the good part of doing the live demo, right? So it's, in the experience, what you will see now is the thing that this board actually behaves as a hard drive. So my PC, without installing anything, recognizes this as if it was a flash stick, basically. There is really no storage on the device. And so if I can change to Carrie's desktop, and if you can actually visualize that on the screen, thank you. So you will see that this board appears on Zoli's laptop as a hard drive called Curiosity. So hopefully we'll pick your Curiosity, and you will want to check inside this drive. And inside this drive, again, I didn't install any software. I don't need special drivers for this. You will see there is a bunch of interesting files. They're not real files. One of them is called Click Me. So I hope you will be tempted to press on the Click Me one. And from there, you will actually see that by default, because it was a .htm file, whatever operating system you have, a Mac, a PC, or even a Linux box, you will see it immediately open the default browser. And the browser will open up on the page that is a special landing page that we prepared, a sandbox. It's part of a sandbox account, but this landing page contains the real experience and has been prepared for us by Google, and actually in particular by Leverage, a partner that has been working with us and with Google to create this ideal experience. So as you can see, actually you can see that the device in particular, the secure element, and this is the unique identifier of that secure element. And so we landed now on this page. This is a dynamic page, and as luck wants, I'll show you now how this page actually changes when we do connect to the cloud. And I have my browser sitting right here. So this is quite a hard test, because we tested this obviously in the room without all of you with your phones on and with all the Wi-Fi hotspots present. So there's 120 more than when we tested this first. Hopefully I will get it to actually connect to the right hotspot. And I'll get to show you some real data streaming on the board. And no, it's not today. So in the last minute, tough luck. I think we'll have to call it a day. So ideally, basically, you would see the blue LED connect directly to the correct hotspot that is actually sitting here, and then a green LED turning on as soon as the connection with Wi-Fi is established. Then a connection to the MQTT broker of Google will happen immediately, and then after that you will see the board immediately blinking a yellow LED. The sequence of color is, if you notice, is the Google color sequence. And then the yellow LED actually represents each packet of data that is being published to the MQTT broker. And then when that successfully happens, as we will not have the luck to see today, you will actually see on your screens, on your browser, you will see the blue line connecting all the way through. And the page actually dynamically, instantaneously will show you the graph with the two sensors data, so the temperature and the light sensor on this board, and it will be immediately animated on your screen. Now, how good would this be if it was just a board and just this part of the experience? You know, the goal here is not only to give you a 5 or sub 30 seconds, that's what we claim, experience and connection to the Google Cloud, but after that, you will want to change the sensors and apply your own specific sensors. So you will want to write your own firmware inside the board, inside the microcontroller on this board. And just for you, if you're not familiar with this particular brand of products, you might have heard, you know, the AVR, that is the microcontroller shown here, is the one that is inside the Arduinos. So most students today coming out of schools and university and out of the hobbyist community are very familiar with that. And so they will want to play with it. And so professional and non-professional developers actually will find a solution that we prepared for them, which is, as Carrie mentioned before, we have a rapid development tool set that is composed of two pieces of software, MCC and START, one for the PIX devices and one for the AVR devices. And with those, literally with a click of the mouse, you will be able to see let me scroll to the correct page. So this is START for the AVR devices. And here you see the blocks composing the project that is actually running on this board in this very moment. And this is available in your browser, so you will do all your reconfiguration of the device on the fly, clicking on each block, changing the configuration. You see the crypto authentication block, that's what controls the ECC 608. So all the software is wrapped in there and templated by that. And so the MQTT IoT block that you see there in blue is the block that wraps the entire communication infrastructure, everything that is needed to access the Wink device, the Wi-Fi chip. And the part on the left where you see scheduler, ADC, USERT, the embedded developers among you will recognize those names. Those are the acronyms of the individual peripherals inside the chip. And so again, you can go there and configure them and select them and make them read temperature, read humidity, read whatever other entity you want to read. And so you can create a complete solution with a few clicks of your mouse, and then hit up there, export project, and just hit the build button on your IDE. And with this, I will give back the mic to Zoli.
Yeah, and please stay on stage. Just very quickly, because we are running out of time, can we please go back to the presentation? Yeah, thank you. So just a very quick summary of the whole presentation. So as I said, there are two sides of the end-to-end security, providing end-to-end security: hardware, software, cloud. Strong IoT security uses secure chip, and then ease of design with a turnkey MCU. So you've seen that 8-bit MCU, which is brand new. And then when it comes to the cloud, simple connection, which we were unfortunately unable to demonstrate, but it is simple, believe me, I saw it. And built-in connect, so I mean built-in into these devices, they can connect to the cloud. And scale, so Cloud IoT provides scaling on demand and also actionable insights using the other Google Cloud tools and services. And with that, we would like to conclude our presentation. Thanks for attending.
Thank you.